Something is a good summary. Let's see how it goes. So the focus, as to be explained, will be on PSDs, TDI response and sensitivity, and it's sort of a continuation of what I talked about this morning. There were many times when I promised I would talk about it in the evening, and I try to put that all in here. So to start off, again, a picture of LISA, and just to describe how the top-level sensitivity of LISA is actually defined. It actually follows from a very simplified principle that you say you have these single-link measurements that measure test mass to test mass separation, and you say you have a target performance in those measurements, that you have two test masses entering in there with some noise performance, and you have one optical metrology system noise, which is just an uncorrelated noise entering into that measurement. And then you build a very simple interferometer out of them, the Michelson interferometer. And that's what you look at to define the LISA performance at the top level. That is highly simplified compared to what I spoke about this morning. But it actually works surprisingly well, and I will try to outline a little bit why it works well. Before I come to a formal definition of sensitivity, I have just one slide. Yeah. Please. Is it on?
Yeah.
It is on. You cannot hear me? I can.
Maybe can you hold
Is it better like this? Yes. I can carry it. It's fine. Yes. So that was your only question. Good. This was easy to answer. So I wanted to briefly give an overview of how you usually think of sensitivity, more in of an intuitive sense. So it's usually defined by an equation like this. You take the noise power spectral density of your detector. I will spend some time explaining what exactly that is. And you divide it by the response of your detector to gravitational waves. I think that was already derived in great detail by Henri in the beginning of the week, so I will not speak much about that. For the noise PSD of the detector, if you take such a simple Michelson, as I showed you before, it looks something like this. You have at high frequencies just your OMS noise terms, and at low frequencies you're dominated by test mass acceleration noise, and the sum of the two follows then, the sum of the two. And you can see that the test mass one actually has some additional structure on top, and the reason for that is simply that you have in each single link not just one test mass term, but two of them. So if you add up a round trip, you have the same noise appearing multiple times, and that gives you the structure that we will come back to later in the talk, how this arises. So this is the noise part. It's essentially just the single link noises with some extra factors. And for the response part, you can compute what we call the sky and polarization averaged gravitational wave response. What that means intuitively is that you just look at different directions in the sky. You compute what is the response to gravitational waves for plus and cross. You average that. You average that over all directions and sum it up. And then you get a curve that looks something like this for Michelson interferometer with 60 degrees arms between them. This is the response in meters. So it's actually a very, very large number just because the arms of LISA are very long, 10 to the 9 meters roughly. And it has this interesting structure at high frequencies. And to get the sensitivity of such a simple interferometer, you then just take the ratio of the two, and that looks like this. And this is very close to what you find, for example, in the Red Book of LISA for the top-level sensitivity curve. In fact, I took here the figure from the Red Book of LISA, and I overlay on it exactly the curve I just showed you. It's just scaled by a factor square root of 2, and you can see them actually match perfectly. So this is the computation that is being done. And I will try to explain why they match perfectly, at least to outline it. But before that, I want to take a small step back and speak in a bit more detail on what a power spectral density actually is, how it's defined, how it's derived. So some details on PSDs. There are a few more slides of math incoming. What PSDs are used for, they're used to characterize random variables, to the statistical properties of random variables. So I try to at least build up the key concepts, so everybody has seen them at least once. I'm sure many of you have seen them many times, but maybe there are some that haven't seen them ever. This is the school. So the basic concept that describes a random variable is the probability density function. The most famous one is certainly the normal distribution. You see up here several examples. And the normal distribution has the special property that it's fully characterized by just two numbers. One of them is the mean, so where your random variable on average sits. And the other one is the variance, so how much your random variable spreads around its mean value. And these are defined via this formal quantity of the expectation value, which for a continuous random variable has this integral, but you can think of it as for a discrete random variable as just taking all possible values and scaling them by the probability that this value occurs. Now, this is just a single random variable. What's a bit more interesting and gets us closer to how we describe these is if you have multiple random variables, so you don't just have a single one, you have multiple of them, you can write them into a vector, and you can still define a mean similar to what you did before, just component by component for each variable. But your covariance now becomes a bit more interesting because you can not just look at how a vector, one of these variables, varies against itself, but you can also look what do you expect to vary, how two variables vary together. And formally, that defines a covariance matrix, which is just the expectation value of this quantity here. You take your random variable, you subtract the mean, you do that for the other variable, and you look at the expectation value of the product. And with that quantity, there's actually also a generalization of this simple normal distribution, which is the multivariate normal distribution, which looks a bit more complicated, but the basic shape is very similar. You have some normalization factor that is now proportional to your determinant of your covariance matrix, and you have up here not just 1 over sigma in the exponent, but you have this product of the noise projected on the inverse of the covariance matrix. Intuitively, what this covariance matrix just tells you is how strongly the random variables vary each individually and how strongly they vary together. And by doing this construction, you essentially project your data onto the relevant axis on which they are uncorrelated. That's one way to think about it. Now, this is for discretely multivariate random variables. In reality, we often, actually not in reality, but in theory, we often deal with something called a stochastic process, which is very similar to a multivariate random variable I just showed you, just that the label is now a continuous quantity. It's a time argument, so you have a set of random variables parameterized by time. The covariance, in that case, generalizes to what we call a cross-correlation function or cross-covariance function, which is simply your random variables taken at two different times. Now, in general, this is allowed to be dependent on the absolute times, but a very useful special case is a so-called wide-sense stationary process, in which this only depends on the time lag between the two variables, which means that your cross-correlation function is then just a function of this one time parameter, the lag, and you take it doesn't matter at which time you evaluate that. No matter when you do your experiment, the statistical properties, at least this one, this second order moment, always looks the same. And this is just a side note that's not really needed, but it's something to watch out for, that in practice, with stochastic processes or with experiments, you usually don't have a million of them and can do statistics at each time step, but you only have one of them. And what you do is that you produce one time series and you take an average of that, for example, to get the mean of the time series. And that works in some cases, but it does not work in all cases. In the cases where it does work, it's called ergodicity, in which case you can replace this ensemble average. I apologize for the notation, by the way. The E and this thing is the same. It means the same. Then you can replace this ensemble average with a time average, like this. And a famous example where this goes wrong is a random walk, where the variance of the thing grows with time to infinity, but the time average grows also with time, but in a different way. Yeah, so this was the time domain measure of these second order statistics of a random process. And what we often look at, because it's quite useful, is the so-called power spectral density. And this is formally defined only for a wide-sense stationary random process. And in that case, there are different ways how people define it, but one of them is to just take the Fourier transform of this autocorrelation function. So you take your autocorrelation and you plug it into the standard Fourier transform. In this case, I already defined the cross-spectral density, so when x and y are not the same quantity, but the power spectral density is then just a special case of that, where the two quantities are the same, and then it's called the autocovariance function, the underlying thing, and the quantity is called the power spectral density. And as I just mentioned, there are at least two very commonly appearing alternative definitions for this. One of them is this one, which is very useful in practice, that you can define this as the limit for infinite times of the Fourier transforms of your underlying functions with a time window applied to them. So you assume your function is 0 outside some time window, take the Fourier transform under that assumption, and take the limit to infinity. And there's another one that's often used, especially in more theoretical texts, I feel, which is this one, that it's defined implicitly, that you take the expectation value of the Fourier transform of your data without any time windowing, and you can then show that it's equal to the power spectral density defined up here times the delta distribution. It's possible to show that these are all equivalent under some assumptions and some regularizations, which I will not go to in detail here. Now, as I mentioned, this definition here in particular is very useful in practice, because in practice we don't have infinite time, we have finite time, and we want to estimate PSDs for finite time series. So what you can do is you start from this finite time Fourier transform, and you discretize it. So instead of doing an integral, you do a sum. And if you then rewrite what your frequency argument is in a particular form, indexed by an index k, and your sampling rate and your total number of measurements, then it turns out that what drops out is exactly what is called the discrete Fourier transform of your time series, scaled by delta t, which is something that is very efficient to compute from time series, which is one reason why Fourier domain methods are very powerful. Now, once you have this approximation for your finite time Fourier transform, you can plug it into that definition of the power spectral density I showed before, up here, where I now also inserted this slightly more complicated function argument, but it's just a placeholder for the frequency. Here, as I just showed on the previous slide, these things, you can replace them with the discrete Fourier transform and the scaling factor delta t. The total time is just your total number of samples times your time step. The delta t's cancel out, and what you're left with is the product of your discrete Fourier transforms normalized by number of samples times the sampling rate. And that's essentially what's being computed if you compute a spectrum with SciPy or whatever, except for a lot of tricks and technical details I will not go into detail, because then this lecture would take a lot longer. So I will not speak much more about it, but I will just show you one example, for one picture essentially, because this is one problem with this estimator is that it, while it does converge towards the power spectral density, it has a very high variance in itself, which you can see in this plot where it just generated some white noise and computed first this estimator you saw on the previous slide. So I just take the DFT and I square it, and then I get this blue curve. You can see that it varies around a lot, and at some frequency there's a little spike going up. That's the signal that I injected there, which is, because of this high variance, what you usually do in practice is that you don't take your full time series to compute the PSD, but you first cut it up into segments, and you compute the PSD segment per segment, which gives you many estimates of the PSD, which all have a high variance. And if you then average those out, you significantly suppress your variance, which you can see here, that the variances of the red curve and of the yellow curves are significantly lower than the variance of the blue curve. But there's a trade-off that you can also see here, because your segments are much shorter when you do that. The frequency resolution of your PSD estimate is also a lot worse. That you can see here by this peak that I injected, that it tends to shrink when I do that, because the PSD, intuitively, it's the average power normalized by a frequency interval. If I have an harmonic signal in there with a constant power, that change my frequency interval goes up and down. And it also gets smeared out, because there are a lot of these technicalities that I mentioned before, like spectral leakage, that the bins, power in one bin affects the readout in the other bin, which is why you have to be a bit careful with choosing your averages and your measurement time in a clever way. Now, that's all I wanted to do for the background of what a PSD is, just to give a brief introduction. Are there any questions on that? Yes?
So which one would you say it's the trade-off between no averages and many averages? What?
It really depends on what your PSD looks like. If it's a very smooth function, you can get away with doing many averages. If it's a very spiky function, you can't, which in turn means you have very bad statistics for your estimate.
Okay, if you want to find peaks, I guess it's better to have.
Yes.
Okay.
Generally, so in all of these estimates, what they injected here is a perfect harmonic signal at exactly one frequency. Mm-hmm. So no matter how long you make your measurement, you will never resolve it because it will just getting higher and higher and higher. But in reality, every signal has some finite width because there's no such thing as a perfect harmonic signal. Mm-hmm. And usually to actually get what we call a PSD, so a measure of a stochastic process, you want to have your resolution good enough that you can resolve that, so that the resolution is better than the width of the feature, which is not always possible. It's like, for example, in LISA, the galactic binaries, they have bandwidths that are, some of you probably know better than me, I think microhertz or so. And in ground testing, we will only be able to measure for a couple of days. So there's no way that we're going to resolve noise features this narrow. Just the reality of how these estimators work. Any other questions on PSDs? For the rest of the talk, the important takeaway is really just that the PSD is proportional, more or less, to the square of the Fourier transform. That's an important property that allows you to derive a lot of important noise transfer functions, how noises couple in different measurements. That's the main thing to remember. So now I want to speak a little bit about how noise PSDs propagate through TDI, so how you come from a PSD at the input to a PSD at the output. And for this, I look just at a very simple example, which is again our single link with uncorrelated OMS noise and uncorrelated test mass noise, which appear in this single link just in a very simple shape, that you have the time series of your OMS noise and the time series of your test mass, of the local test mass, and the time series of the test mass on the other side of the link with a delay. And actually this general shape that you have a sum of noises with some delays in front, that's almost universal in the noise modeling that we do for LISA, which is why I want to briefly single out how to model it. It's very easy. These delay operators, if you take the Fourier transform of a time series that has a delay applied to it, you can just write it out, and you can do a coordinate substitution to move this delay into your argument, and you immediately get out that your the Fourier transform of the delayed quantity is just equal to the Fourier transform of the original quantity with a complex phase applied to it. So whenever there's a delay in these equations, you can just immediately replace it with a complex exponential. Which means, in our case, for the single link, taking the Fourier transform, going to the frequency domain just means putting a wiggle on top of everything and replacing this d with an exponential. Now, for the case of TDI, here's a very brief summary slide of what these data combinations look like. A lot of symbols, but they're actually very easy symbols. So I'm using a shorthand notation for these delay operators, that if there are two of them following each other, I combine the indices if the internal index matches. So for example, this D131 is actually a D13, D31. It's just a concatenation of two delays. And then it turns out that these different TDI combinations that I spoke in the morning, they are kind of related by extra factors in front. So the zeroth generation Michelson, the very simple one, doesn't have any factors in front. It's just a local measurement plus the distant one delayed, minus the other local measurement, minus the other distant one delayed. And for the first generation TDI, you just have these extra loops in front of the left arm and in front of the right arm. And for the second generation, you add even more loops in front of the left arm and in front of the right arms. Now note that in general, these loops have different delays because you have to delay them by different light travel times, but it's often being done to just assume that all the delays are equal, because in that case, these expressions simplify drastically. you can then just factor all of these delays out, and you just get this relation that the second generation is equal to the first generation with such a thing in front, and that's equal to the 0th generation with another of such delay differences in front. And if you now take this expression and you move it to the frequency domain, these delays, they again just become complex exponentials. And if you now want to compute the PSD of such an expression, you, again, it's roughly proportional to the squared magnitude of the Fourier transform. So you have to compute the squared magnitude of the Fourier transform of this difference. And if you've, it's easy to do that. And it turns out that that gives you these sine squared factors that you saw at the blackboard in the morning. That's what I meant on this slide, that you have to modify the requirement that you compare against. These sine squared factors that are applied here, they are just these absolute values of these complex exponential differences. And the nice thing is that under this assumption, the arms are equal and that you only consider things that directly enter in the single link, everything gets this factor, which means that the sensitivity of second generation TDI is identical to that of 0th generation TDI. So for sensitivity, for performance modeling of the instrument, and for also a lot of data analysis, in that assumption, you don't really have to care about it at all. Now, the problem is that that's, of course, a lot of approximation in there. This does not hold anymore exactly if you consider unequal arms. And it also does not hold anymore for noises that don't enter directly in the single links. In particular, this clock noise correction that I tried to explain this morning does not enter like that, and it does not get this transfer function. And then it suddenly makes a difference, because then you might get noises that fill up those zeros and destroy your sensitivity. But I have an example for that later in the talk. Now, this was for a single TDI channel. Now, of course, in reality, we don't just use one channel, but we typically use at least 3 of them. And in that case, if we want to do data analysis, we need not just a PSD, but we need the full cross-spectral density matrix. This is a frequency-dependent thing, so this looks different for each frequency. And in principle, a priori, they can all have different entries. The PSD of X and Y and Z, they don't need to be equal. And the cross-spectral densities between them, they also don't need to be the same. However, it's very useful if they are, which is why it's a very commonly made assumption that the cross-spectral density of the channels actually looks like this, that you have the same PSD in X, Y, and Z, and you have the same cross-spectral density between XY, between XZ, and between YZ. One ingredient to get this shape is to assume equal arms, because if you don't have equal arms, the symmetry is broken. But another one is that the individual PSDs of all these noises entering your measurements, that they are exactly identical in all spacecrafts, which is not very realistic. That will not be the case, but it's very useful for the reason outlined on the next slide. Because in this case, if you make that assumption, it actually turns out that it's very easy to compute the eigenvalues of this matrix, which are just these guys. So you have 2 that are the same, and 1 that is different. And you can also compute the eigenvectors of this matrix, or equivalently the combinations that you have to apply to your data to get uncorrelated channels. And it turns out that they are completely independent of what your noise actually is. You have this very simple form of A, E, and T, whereas A and E actually form a subspace in that sense. They correspond to this degenerate eigenvalue, so you don't have to use exactly those. You can use other sort of rotations around the T vector. But the T1 is a unique direction that forms this other subspace that has much reduced sensitivity at low frequencies. Which is why this is very tempting to use this approximation, and because it really simplifies everything a lot. But there's actually a lot of approximations that go in there, and in general, this does not hold in reality. Now, this was about PSDs and PSDs in TDI. Are there questions on that? Yes?
I saw in the PSDs, and I guess because of the fact that you're multiplying by a sine function, that the PSD goes to 0 at certain frequencies. Is that not a concern for the data analysis? I mean, I remember dividing by the PSD at some point.
Yes, I mean, in principle, it is a concern, of course, because it becomes ill-defined, the
Yes.
inverse. But strictly in that assumption that only happens at a singular frequency.
Mhm.
So if you compute an SNR or something, you integrate over frequency, you can just exclude that point and it doesn't change anything.
Yeah, okay, but in practice, already if you're reaching machine precision, you should already
Yes,
get rid
in
of the
practice,
frequencies.
you expect that there's some artifacting, at least from numerical precision, around those points. In practice, those points are also not exactly there because the arms are equal, so you have overlapping sine squared with different, the arms are not equal,
Mhm.
so you have overlapping sine squared with different zeros, so they're slightly
So in
moving around.
the unequal arm case,
Uh-huh.
those zeros disappear.
Yes.
Or you get more of them. I
Yeah,
don't know.
you get, yes, they smear out, you get
Okay.
overlapping ones from noises and different signals.
Mhm.
And there's this extra complication on top that you also have noises that just don't have the same one and fill it up.
Okay.
By the way, I prepared less slides than this morning, so please feel free to ask questions and discuss. Yes, so if there are no more questions.
Sorry, I also have one. Can you still use the AENT channels even if you don't have all these approximations that you can make, and at least have like basically like a reduced correlation in there, or does it just not work at all?
So it breaks very strongly for T. So T you really should not use without those approximation. For A and E it's not that bad, except at the zero frequencies, where it's still pretty bad. Maybe I can quickly go out of the presentation and show you a plot from a paper we did, which looks at exactly that question. So this is, here I show you the cross-spectral densities between different channels, and nominally this should be zero for A and T, and you see that for the cross-spectral density between A, T and ET, they're very much not zero at low frequencies, they become huge, whereas the one between A and E are actually still pretty small, although this is for first generation TDI. I think for second generation it's about twice as bad, so it might even become relevant for A and E in that case. And at high frequencies around the zeros, you also have to be careful because there it becomes completely messed up. Let me go back into the presentation. Are there more questions on that? Not, I will try to outline how to actually go from the PSD to a sensitivity curve. So, because the PSD, of course, only describes the noise of the detector, but we want to somehow characterize the performance of the detector in something that takes the response to gravitational wave into account. And to derive that, let me maybe get everything on the screen. It's derived from the optimal SNR of a matched filter. In case you are not familiar with it, it looks something like that. So you have in there your inverse of your noise covariance matrix, and you have in there your Fourier transform of your signals, which in this case I allow these to be also stochastic themselves, which is why there's an expectation that you want them. And then the whole thing is just integrated over frequency. Now to derive a sensitivity, what we can do is for our signal, to write it in this form, where we have our strain in the Fourier domain. I think the strain in the time domain was derived in detail by Henri. And that is how, so you have your strain in some global frame, like in the solar system barycenter. To get this response matrix, you first need to project it onto single links, and I think that was derived by Henri in detail. And you can also find a frequency domain derivation of that at this reference here. I will not repeat it here. But then there's an extra step that you project it onto your TDI channels. And luckily, within the approximation in which all of these sensitivity calculations are done, which is stationarity, that step is conceptually very simple. You just have extra complex exponentials that you apply to your measurements, and that's it. And this response matrix then contains both of these parts. It contains the projection on the links and the TDI part. You can then rearrange that, so you essentially just, I should not have done this with, so your X that appeared here, it's the response matrix times H, and if you insert that here, and assume that your underlying strain has some properties, in particular that it's the power is equal in the H cross and H plus polarization. And then you can simplify the expression to look like this, and you can do some algebra to rearrange it to show that this is actually the trace of the inverse of the covariance matrix times this response matrix. And this is, in principle, you can do that for gravitational waves coming just from one sky direction. But once you have it for one sky direction, you can sky average the result, and then you get the sky averaged since SNR squared. Since the noise does not depend on the sky direction, the only thing that gets sky averaged is the response, and you get to this expression. And the sensitivity is then simply defined as the inverse of the argument of the SNR squared. That's me. I got a bit of an DF at some point. I'm sorry about that. That got dropped. So it's sort of the how do you say, the power your background would have to have such that you get unit SNR per unit frequency. That's the intuitive explanation of sensitivity. And the slide is also very messed up, I apologize. And in practice, there's one important special case, which is that you have uncorrelated channels if your covariance matrix is diagonal. In which case this trace that I spoke about before simply becomes the sum of the individual sensitivities, because your covariance matrix is diagonal, so this is just just picks out the corresponding components, and then you can look at them independently, which I do in this plot. So you see here at the very bottom the combined sensitivity curve. So that is the total expression that we have on the left-hand side. And on top of that, you see the sensitivities of A and of E, computed in a simple scenario that you have 15 picometer per root hertz for the OMS and 3 femtometer per root hertz for the test mass in the yellow curve. And you also see the sensitivity of this T channel, which is much worse at low frequencies, which is why we call it a null channel. But one thing that even in this approximation, you can see that at high frequencies, the sensitivity of T is actually equal or better than that of A or E. So if you're interested in sources in that frequency band, you should not discard the T channel or the third channel in general. But of course, in realistic scenario, T is not so simple. You have to do a more accurate, you have to use the full covariance matrix. And this also explained this factor 2 that appeared in the beginning, and also this morning, because it turns out, if you do the calculation, that the sensitivity of X is actually equal to the sensitivity of A and the sensitivity of E at low frequencies. So this sum up here simply becomes sensitivity of X over 2 plus sensitivity of X over 2. Oh, yeah, other way around. But so you simply get 2 times the sensitivity of X plus 0, because T doesn't contribute anything. And that's why that is being used since a long time for characterizing laser performance, but it's not quite the full story. Now, for getting a bit to the full story, I have at least an example. As I explained this morning, we made a lot of approximations in what I just showed you. For one, the arm lengths, they're not equal, but they are time varying. They look something like this. I saw that this morning. And we also have not just laser noise and 2 noise components, but we have many noise sources, some of which have complicated couplings and non-stationary coupling coefficients. And this L0 pipeline does all of those combinations, reducing all of those dominant noise sources. The most of them, like spacecraft jitter correction, TTL, and all the primary noises, like shot noise and so on, they do enter on the single link level. So this basic logic for TDI holds for them, but not all of them. In particular, this clock noise correction, I had that in the slide this morning, that it's an extra term you add afterwards, and you cannot express it as something that you already do in single link level. It changes depending on what your TDI combination is. And in addition, it's also non-stationary, so the coupling factor for all the noises that you use in that correction, it goes up and down based on this frequency plan that I also mentioned this morning. Now, how do you now model this? with increasing complexity, you can, in principle, use exactly the same expression that I derived here, this guy, which is more general than what you usually find in LISA literature, because it accepts a general noise covariance matrix. And what you can then do with that expression is that you consider a big covariance matrix for all of your fundamental noises. So in this, I have here a prototype script. This is now moving more into active research territory. So take this all with a grain of salt. In this prototype, I consider 63 different noise sources, which are individually assumed uncorrelated on their own, but they appear correlated in the measurements. This example doesn't have TTL, but it doesn't change the global picture. I then project these noises into the covariance matrix of the raw measurements. So I have a matrix for the, not just for the single links, but for the interspace cut interferometer, the reference interferometer, the test mass interferometer, the sideband measurements, all of those go into a big matrix. And I compute how do these noises, how are they correlated in that big matrix. And then we can further project that into our TDI variables with or without clock correction. And we do the same for the signal response. And then we evaluate our sensitivity expression. And of course, all of that is under somewhat unrealistic assumptions. For one, I assume stationarity, which I know, at least for the laser noise, is not a good assumption at all. And another one, just for numerical precision in the current tool, I had to reduce the laser noise level, because otherwise it explodes the double position variable very easily. And also the noise levels that I assumed, they're not really the latest current best estimates for all the hardware, but they're simplified models as we are using them in the instrument simulator. So it's somewhat comparable to what we will have for the next common data set, but not the real numbers. And if you do that, you get something like this. So this is a cartoon, more or less, where I show the power spectral density, or rather the sensitivity, sometimes also labeled strain ASD, either for TDIX, if you don't do clock correction, or for the combination of X, Y, and Z using the full covariance matrix, again without clock correction. And on top of that, I also show X with clock correction and X, Y, Z without clock correction. And you can see that it's moving around quite a bit. Note that it's a bit fake, because I have a finer time resolution here than the data actually had. I only computed it on a 30-day time grid and then interpolated. That's why it changes very suddenly. But the basic features, they are real. So you have, or at least I think they're real. It's still preliminary, but I assume so. And the things that are interesting, I think, about this, for one, of course, you have all these spikes at high frequencies that are moving around, that are going up and down. And I have another zoom in on that in a bit. But you also have, if you don't do any clock correction, you have these in this combined TDI XYZ. You see that it sometimes at low frequency actually approaches the normal sensitivity, which seems to indicate that there is a way to correct clock noise in between X, Y, and Z without using the extra measurements, which is interesting, but I haven't investigated it further yet. Now for those high frequency spikes, I also find it useful to zoom in a little bit. So here you can again see the same plot, just zoomed in at the high frequencies. And you see that the spikes are actually in slightly different positions for X, Y, and Z. And the reason for that is simply that the zeros are in slightly different positions for X, Y, and Z. The main cause of these spikes is, again, noise in these clock noise correction variables that fills up the zero. And it does not, so your noise does not go to zero, your gravitational wave signal does, and your sensitivity explodes. But one thing I find interesting is that the combined sensitivity of TDI X, Y, and Z is actually a lot better than the individual ones in these points, simply because the zeros are at different frequencies. So although your sensitivity explodes for X, Y, and Z individually, there's always, most of the time, one of them that's still kind of okay, that pulls it down again. Although I think for practical data analysis, it's probably still a very ill-behaved thing. You run into all those problems you mentioned before, that the dynamic range is very high, and it's probably not advisable. There's also a curve in here that I label sensitivity for more measurements, which is exactly what I mentioned before, that I don't actually compute TDI, but I just use my full covariance matrix of all my measurements, and I use how my gravitational wave signal appears in all my measurements, and I directly compute the sensitivity. So that's the theoretical optimal data combination you could do. Again, under somewhat unrealistic assumptions, so it's sort of a best case lower limit, and that's that dotted curve. which luckily tells us that this is indeed seems to be an artifact of TDI X, Y, and Z, of that particular choice of data combinations. Yeah, so that was this example, and this actually probably brings me, I think, to my last slide. So we were faster than expected. Not bad. There's a question.
Are these first or second generation TDI?
Second.
Second generation, okay.
So here you said that, like, since in the optimal sensitivity from raw measurements, you don't see some of the peaks, so you are saying this might be the artifacts from TDI. But there are also cases where, also in this sensitivity from raw measurement, you also see some peaks. So what's the origin of these peaks?
Yes, indeed. You do. You also. I think these are just due to the fact that the zeros, like the gravitational wave signal, does not have exactly the same correlation in the single links as the noises do. Which means if you have unequal arms, the noise will have its zeros at slightly different places than the gravitational wave. Which means, where that is the case, that your gravitational wave is stronger suppressed and your sensitivity goes up. That's my intuitive understanding, at least. It's very good. This is very soft.
Yeah, maybe you're talking about this, the zeros in the response itself. Keep in mind that this is sky average, and so it's not really representative of what's going to happen if you look at one source in the sky. So one source in the sky will have better defined zeros.
Yes.
And so the sensitivity from these raw measurements will probably look a little bit different around those frequencies.
Yes, that's exactly right. I mean, the sky average sensitivity that we look at here, it doesn't have any zeros. And the one for a single source direction does. So, yeah.
Could you explain again the lower curve sensitivity from raw measurements?
Yes, so it's to compute this, I have to go back to the slide. I evaluate exactly the same expression. It's just that this covariance matrix is not the covariance matrix of 3 TDI channel, but it's a covariance matrix of 30 measurements, including laser noise and clock noise and all the secondary noises and spacecraft jitter.
Okay. So that would be a theoretical global fit that would be using L1 data, L0 data, L0.5.
Yeah, I wouldn't really call it a global fit because you're not fitting anything. It's an optimal data combination.
An optimal data combination.
Assuming that you know how your noises enter into your measurements, you know how you have to project the measurements to get the optimal sensitivity.
Okay. And in the plot you showed with the full, without zooming in on the higher frequencies, looks like the clock correction is making a huge difference, and with it you don't get a lot of variation. Like the red curve is not changing much.
Yeah, I mean it depends on the channel, I think. So if you look just at X on its own, it doesn't change much with or without clock. What changes a lot is the combination of X, Y, and Z, which would imply that at low frequencies you can cancel the clock noise that is individually limiting X, Y, and Z between the 3, at least at low frequencies.
But these are two, what kind of noise do you do? Because at low frequency, I think just noise. No, I was just wondering, so what kind of noise did you put there? Like test mass, OMS, and so on. But it's not just, I mean, I'm not an expert on clock noise, but at low frequency maybe just because the test mass is dominating. So somehow the clock noise doesn't really...
I mean, the test mass, it's dominating in this case at this sensitivity for more measurements curve. So this is the sensitivity that you would reach without any laser noise and any clock noise.
No, yes, I mean, they combine TDI X, Y, and Z without clock noise. Is that test mass there inside too or not?
Yes.
And so I was wondering, the fact that somehow it reached the other channels is because the test mass low frequency is dominating for the channels.
Yeah, now I understand, yes. The reason why it reaches this exactly the same level is that it then hits the same limiting noise source.
Yeah, so I mean, it's not that you can cancel the clock noise, I assume, just because at that level just other noise are dominating.
Yeah, but I mean, you do improve the sensitivity significantly from just looking at a single channel. Okay, we can discuss about it later. There's another one. Yeah, we do have time.
Maybe this will be covered in a later data analysis lecture, so let me know. But is the data whitened in a way similar to how it's done for LVK? And if so, like, how long of a stretch of data, and what is the PSD that is used for that, sort of?
I mean, the whitening is kind of included in this expression, I would say, because you normalize your response by your signal covariance, which is kind of what whitening is. But I don't show you any simulations. There are no time series. This is all computed directly in the frequency domain. So these are all just models.
Okay. But sorry, so then practically, like, is it sort of decided how long of a stretch of data will be used at a time to estimate this PSD, or?
I don't know. I'm not in the L2D. I don't know what people are planning. I mean, this assumption, at least for characterizing the noise, this assumption of stationarity, it's not super good. It will not hold for the full mission duration. It's probably, hopefully, okay for a couple hours, maybe a couple days. More questions?
Maybe it will come back on later, but how important would it be to not use this stationarity assumption? Because say I want to study a signal that is in band for the full 4 years of the mission, then I cannot use a simple PSD, I guess.
I don't know, I must say. I hope we find out with the next common data set where we plan to include many of these effects, and people will be able to tell. I think that the best way to answer these questions is to generate data that has these properties and see what happens. JD, maybe you want to?
Yeah. I mean, again, I'm not the best expert in data analysis, but what's clear is that for long-lived signals like galactic binaries, all the works that were published up to now with kind of realistic noise shapes did cut the data into segments of maybe a couple of weeks, and then analyze those segments, assuming local stationarities in those segments. I think you
well, actually, I think for galactic binaries, we actually do the average over the year. So we cut in frequency, not in time.
That won't work, I think.
Yeah, I mean, yeah, we have to find out, I think. I mean, where things almost for sure will go wrong is at high frequencies. So people looking at stellar origin black holes, they probably need to worry about this more than maybe people looking at galactic binaries, because you can see that this curve, it's actually not moving around much. So it's like the non-stationarity from the binaries themselves is a lot bigger than this.
No.
Can we simulate realistic evolution of the noise?
We can simulate more realistic evolution of the noise.
And we'll keep getting better at that, I guess.
Yes. So
I think that's good.
Yeah, I mean, for the I agree.
No, I mean, like, I might have eaten some words in my head there, but like, okay. Because if you're able to simulate realistic noise, sure, writing a likelihood can get a little hard, right? If the noise keeps changing with time. One way to do it is to just chunk up the data. And if you're doing parameter estimation, for example, you could do a condition. You can do like an autoregressive kind of probability. You say, from this data, I get this posterior. I'm using that as prior for the next chunk of data, and then you can do that. That's one example, I guess. But
yeah, yes.
So it's not impossible as long as we're able to figure out how to. Okay.
I'm not trying to say it's impossible. I'm just trying to say
as in we don't need new methods necessarily, I would think.
Okay, depends at which point you call it a new method.
True, I guess. Now I'm talking about chunking up data. Unfortunately,
yes.
No.
You can't just take a Fourier transform of your full data and do that. It's,
no.
It might be worth mentioning, there's a lot of traction, I think, in the data analysis people in LISA to work in time frequency representations that might accommodate a little bit better those slowly varying non-stationarities.
Also, one thing I want to mention, in this plot, I still assume that all the underlying noises themselves are stationary. They will not be in reality. They will also not be in the complex data set for the next DDPZ data set. We will include some physically motivated non-stationarities there as well, which might make it more complicated. I don't know.
So another way to say it is all the non-stationaries that we see here are just coming from the TDI transfer functions, ultimately coming from the orbits.
Maybe on a tangential, do we have ways to, like once LISA is flying, to estimate the noise that different components are introducing? Because you will not have empty data stretches, right?
It's very difficult.
Okay.
I mean, I think it's a very difficult question because, as you say, you don't have empty data stretches. There are all these pesky gravitational wave signals in there. And you do have a null channel, but the problem is that it's sensitive to other noises than your sensitive channels. So that doesn't really solve the problem either. So it's a difficult problem. You will have some priors on what the instrumental noise will look like because we have some things that we know are there. We have an estimate of how big they are, but we don't have a complete picture.
So you might, in your analysis, actually have to give priors for that and fit that together.
Yes.
With
Just to touch again on the non-stationarities, we were also to deal with gaps that will force us to cut into some chunking data anyways.
Yes.
So
that is correct.
We were to do it regardless of.
Is the possibility of having another space-based detector in a similar frequency range, would that
That would be great.
That would help you.
No, that would help greatly because for one, of course, it helps greatly because you get much better source localization.
Exactly.
But it also really helps you to tell, is this instrumental noise? Is this,
yeah, exactly. That's what.
Yes, that would be great.
If there's another mission and we get the data publicly.
Yeah, that's true. And live. Say that again.
Are you paying for it?
I mean, I'm thinking about it.
Yeah, so if anybody has a couple billion euros lying around, please invest them. Are there more questions on this? Otherwise, I do have one more slide. I can maybe finish, and then we can have more discussion if you want. Which is this one. Okay, so more of an outlook. As we just discussed, the precise impact on the data analysis of all of what you just showed, it needs to be studied. And again, good way I think to do that is to include as much as possible of these things in the DDPZ dataset. The height of these peaks, it also depends on the offset log plan that I spoke before, so it might be that you can do some optimization to reduce the impact of what we just saw. And as I mentioned, the specific shape of these curves, it depends on the DDI combination you're using. Here's, for example, a picture where I did the same kind of simulation or computation using not DDI XYZ, but different DDI channels, Sagnac-like ones, C212. They were in this very big table this morning. I'm sure you all have it perfectly memorized. And you can see that they are much better behaved at high frequencies, although you can also see that they are slightly less sensitive at low frequencies still. This is not necessarily the perfect answer, but it just shows that you have some freedom there what you can do, and you can explore different approaches. Another one is to use this method DDI infinity that we spoke about in the morning. That should also be somewhat robust against these phenomenons because it also sort of finds an optimal solution. Yeah, but there are things we can try beyond Michelson XYZ. I think that's my last slide.
Any questions?
How do you deal with transient glitches or something like that?
Sorry?
What if you have these artifacts like these transient kind of a glitch that just comes up in time?
Completely out of scope of this talk, but I mean, in principle, they're
like
not well described by a PSD because they are not stationary at all. And I think the typical approach is to fit them and to include them in a global fit.
I just wanted to comment because we have been talking about non-stationarity of the noise, that all these non-stationarities here, they are coming from the orbits alone. In the actual data set, you are going to have millions of galactic binaries and, of course, things rotating and so on. So the big non-stationarity that you really see by far is the galactic foreground. This is kind of a secondary problem, let's say, from the data analysis, from the L2 point of view, in terms of non-stationarity.
It really depends what you compare against, like in which frequency range you look at. Of course, if you look at 2 millihertz, yes, the galactic binaries, they will be the dominant thing. If you look around the zeros, you don't see the galactic binaries anymore, but you're... And it's not really that your noise is going up and down that much, it's just that your signal response is going to zero in certain points, and that moves around very quickly, so it's this...
Also, so if you're talking about the galaxy, if you have some models of the shape of that galaxy, we know exactly how LISA is facing it, and it's something that you can model. Of course, it's something that probably will be fitted, but it's like the noise, which is very hard to measure and have models of.
Yes, I mean, also, it's also not in the slide, and I'm not sure if it will be in the next data set, but at least the whole low frequency part in LISA Pathfinder, which is the only comparable experiment we had, they had a huge non-stationary unexplained noise that went up by a factor of, 2 or 4 in power over time, and it's not clear why. So we have to see what happens with LISA. Lina?
Yeah, if there are no other questions, that's exactly on time. Thanks again, Olaf.